It's nice to see you all again. And today we'll discuss regarding modern control engineering, some more parts in modern control engineering. And let me share my screen. It's visible, I think. So this lecture talks about solutions of state equations. We have discussed what are state equations in previous class. We have talked about state space analysis, their introduction, their advantage, how do you represent them in general, and what are their generalized representation if we, and also the representation in linear systems. And how do we see multiple inputs when we write state space model for any particular physical or electrical or mechanical or any type of system which we are considering. So that this is that, and then the block diagram representation of that state space model, and also the signal flow graph representation of that state space model. We have taken several examples and then solved for the differential equation, and then converted those differential equation into a state space model in the last class. We have also seen a spring mass damper system and then converted its differential equations into the state space model. So as now we know how does the state equation look like, it is also important to understand how do we solve these state equations. So if we consider these equations and then we try to solve it. So let's consider a first order differential equation. So I'm considering a first order differential equation which with the initial condition being x of 0 is equals to x0, and my differential equation looks like dx by dt equals to ax with the initial condition this. And if I keep it as equation number 1 here for today's class, and so I'll do a little bit of rearrangement and I'll rewrite this equation as dx by x and a dt. I think I can do this. So that's my equation number 2. And if we are integrating this equation number 2, then we will, so on integrating this equation 2, I'll get is that log of x equals to a t plus c. If I further solve this, then I'll get x equals to e to the power at plus c. This is t, this is plus c. Okay, so I can further go and write this as e to the power at multiplied with e to the power c. Okay, so now when we know that we have a initial condition, right, and that says that at t is equals to 0, from this equation number 3. Okay, so for this equation number 3 at t is equals to 0, we will get x is equals to at x is equals to 0, we will have the value as e to the power c. Equation 3 can be rewritten by putting the value of initial condition, and then we have this here. So as we know now, we know that our initial condition is this, and e of c is equals to x0. Okay, so this is now we will substitute this initial condition and we'll try to find out the solution of first order differential equation, right? So by using these two solutions, we have x of e to the power at multiplied with x0 from here. Okay, you can write this, and e to the power at is from this. Okay, so by using the t is equals to 0 in this, we get this equation, and we use this equation again in this equation, and we get x is equals to e at x0. Okay, and now we know that your exponential e to the power x, like we have e to the power at here. So just to know about how do we write an exponential term, so e to the power x can be written as 1 plus 1 plus x plus 1 by 2 factorial x square plus goes on and on and on. And I can write the last term as 1 by n factorial x to the power n. So that's nth term. It can still go on and on and on. So it's a series of the exponential function. So now we'll be using this information to further solve this equation. As we know that this is the exponential expression. So now we can write something for this particular equation, right? So now we will use this information for this equation and we will rewrite it again. So x can be rewritten as e to the power at x0, where your e to the power at is 1 plus at plus 1. This is t, at plus 1 by 2 factorial a square t square plus 1 by 3 factorial a cube t cube. So this can go on and on and on. Okay, and the last term, if I want to write, I can write it as 1 by I factorial. This is I factorial, like this, I factorial a to the power I t to the power I, and this can go on and on and on. So this is, I'm closing it here. So that's my e to the power at, and it's multiplied with x0. Okay, so this was for the case of a scalar equation. Okay, so here we had a scalar quantity in the differential equation and we solved it for this, and this is something like this. Okay, so if I want to keep it like equation number 4 and then equation number 5. So equation number 5 is my solution for this particular equation number 1. So this first order differential equation with the scalar quantity here can be solved like this. But if we have a input vector, okay, we consider a state equation with input with the state vector. Okay, this was scalar state, only x was there. But if we have a column of state, for example, x1, x2, x3, x4, then what will happen? Then obviously your state matrix will come into picture. So here we only, this A was the coefficient for your scalar system and it got expanded into the series. Okay, so if you, when you will have a state equation in a much larger version of this particular equation number 1, so that would be something like, okay, so I'll just keep it here and I'll write it here. So right now we are not considering input here. We'll solve the input, state equation with input later on. Right now we are considering a homogeneous state equation, which is x dot t is equals to capital A of x of t. So this is your capital A is your state matrix. Here it is a square matrix, n by n state matrix, and it's E of xt, and the initial condition for this is x0 is equals to x0. Okay. Now this is your initial condition vector. It's a vector. This is also a vector, and this is also a vector. This is also a vector, and this is your square matrix. So if it's your column vector, you will have, n cross 1 column vector, something like that. So similarly, the dimension of this and this will match, and so as this and this will match. This would be your n cross n square matrix. So by analogy from the above solution, we would just like to continue, and we would like to write the solution for this matrix or vectors equation as per the equation number 5. So our x of t, so your x of t is nothing but the solution for this one, right? So x of t can be written as a0 plus a1 t plus a2 t square plus a3 t cube plus go on and on and on, and plus a I t I, and plus it can go on and on. So I can write it as equation number 6 for our better understanding, and then we have all of these A's are nothing but these are the matrices, and all of the elements of these matrices are constant. So A0, A1, A2 till AI all are matrices. Matrices which are constant. Okay, and so now when we have this equation number 6, if we differentiate this equation number 6, differentiating equation number 6, we will get a capital, sorry, let me write it properly. We'll get x dot. Okay, so we had xt. Xt is written as this in the series form, inspired from the above solution, and now we are differentiating this, so we'll get this. Okay, so if we differentiate this whole right hand side of this equation, then we'll get it as a1 plus 2a2t plus this is plus 3a 3t square plus it will go on and on and on. So similarly, this term will be differentiated as I of a I t to the power I minus 1. Okay, and plus it will keep on going ahead. So keeping it as equation number 7, and now we are multiplying equation number 6 by a. Okay, so if we multiplying equation number 6 by a, so we'll get it as a of xt. So this xt and this xt is same. It's a vector. It's also a vector. So a of xt is equals to a of your a0 plus a1t plus a2t square plus go on and on and on plus your ait to the power I, and it can just go on and on and on. So that's your, I'll write it as equation number 8. And now from equation where we have considered this, from this equation, we know that your x dot is equals to axt. So we can equate the coefficients of equal powers of t in equation number 7 and equation number 6. Okay. So equation number 7 and 6, we have several equal powers of t. So let me just clearly write here that we can equate the coefficients of equal powers of t in elements, in the equation, right? So I can directly write it as in equation 6 and 7. Okay, so now we will equate the whole thing. So let's make a straight line, and if we equate on equating constants. So let me also try to keep the 6 and 7 in the view if possible. Okay, if we equate the constants. So now if you equate the constants, then your A1 is equals to AA0, right? So here, so sorry, actually here it was not 6 and 7, it was 7 and 8. We have to equate it by 7 and 8, not 6. Actually 6 is already we have obtained the new version of 6 as 7, right, by multiplying a here. So, and as we know that x dot is equals to axt, so we are equating that, and we obtain this from also this. So it's just like it is what we know, but we are writing it in the series form and then trying to obtain something, right? So if we equate 7 and 8, so our first comparison would give us A1 is equals to AA0, A1 and AA0. Okay, and the second part of equal powers of t, so t is here and t is here. So if I compare these two terms, so it would be AA1 equals to 2A2. So it would be 2A2 equals to AA1. Okay. So I can write from here A2 is equals to half of AA1. Okay. Now if we put the value of A1 from here, this equation, then it can further become A is equals to AA0. Okay. So I can write it as half of A square A0. So this is the term which is becoming like this. So if I further equate the t square terms, okay, so this was for t, this was for 0t, and now this is for t square. So if I compare the t square part, then 3a3 is here and a2 t square. Okay, so 3a3 is equals to a2. Okay, and a3 can be written as a1 by 3 of aa2. I know the a2 from here. Okay. So So I can put that A2, this A2 I know. So I'll put this A2 1 by 3 A into your half of A square A0. So if we see, finally we can write it as 1 by 3 factorial and A cube A0. So if you keep on doing this, then for the ith expression, for this expression, we'll be able to obtain something like this. AI equals to 1 by I factorial A to the power I A0. So basically we are writing the ith term in the as the terms of its previous and the combination. So it's a linear combination of its previous terms. Your AI term is the linear combination of previous terms. So in this analysis, what we are doing is that we are understanding this fact that all these matrices A1, A2, A3 can be expressed in terms of A and A0. So this expression would replace A1, A2, A3 till AI in the assumed solution of x of t. And your equation, this equation, your equation number 6, okay, your equation number 6, this would have a solution in terms of A and A0. Okay, so if we would like to write that, okay, so therefore your x of t can be rewritten as A0 plus A0t plus 1 by 2 factorial. This is t, this is plus 1 by 2 factorial A square A0 t square, as we have obtained this, right? Plus 1 by 3 factorial A cube A0 t square. So it will be your cube, t cube, plus it goes on and on and on, and it will go till 1 by I factorial ai A0 by t to the power I, plus it will go on. So if you would like to take A0 as common, and then you can again write this as 1 plus AT plus 1 by 2 factorial A square t square plus 1 by 3 factorial A cube t cube plus dot 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 goes on and on 1 by I factorial A to the power I t to the power I. And does it looks like something familiar? So here your I is nothing but it's a unit matrix. Okay, if you want to solve it, then also we can with I it will be just multiplying 1. Okay, so for as we had equation number 8 up there, we can keep the number here as equation number 9. And when we have equation number 9, where your I is nothing but a unit matrix. Okay, and as we know that, so now this is your solution for x of t. Okay, and as we know that when your t is equals to 0, your x of t would be x of 0, which is x of 0, which is initial condition. So now from this equation number 9, when t is equals to 0, we get x of t at t equals to 0, which is x of 0, and that is what? That is nothing but a0. Okay, so that we say that's your equation number 10. And now if we combine equation number 9 and 10, then we are able to write it as a0 is equals to x0. The initial condition is nothing but a0. So now if we use this information from equation number 10 and we substitute this into your this solution of equation number 9, then we will have a reworked form of x of t, which is nothing but x of t is equals to 1 plus a of t plus 1 by 2 factorial. This is plus, this is t. 1 by 2 factorial a square t square plus 1 by 3 factorial a cube t cube, which is more on and on and on, and then 1 by I factorial. This is factorial, this is I. Okay, I factorial, and then a to the power I, t to the power I, plus go on and on. And then what we have done from here, we have replaced it as in the form of initial condition x0. So that's your final solution. And there is something more about this solution, that each of the term inside the brackets is your n cross n matrix. Okay, and so all of these each A's, these are n cross n matrices. So this x would be accordingly. Okay, and this all the multiplications will happen accordingly. And because of this similarity of the entity inside the bracket with the scalar exponential of e to the power at, which we have seen earlier in this case, equation number 5. Okay, so we will have a, I mean, that's the scalar exponential. This is scalar exponential. So we have seen that already. Okay, so now we will have what? This whole thing, if we write in the form of an exponential, then that would be known as matrix exponential. So here your one topic of matrix exponential is getting done. So that's here your matrix exponential, and how you would write that matrix exponential, e to the power at. So your this A is a matrix. Earlier you had a scalar quantity here in this exponential term. Now here you have a matrix quantity here. Your vector quantity, rows and columns, n cross n, n rows and n columns here in this matrix, and that's going in the exponent. Okay. So e to the power at will be written as your 1 plus at plus 1 by 2 factorial a square t square plus 1 by 3 factorial a cube t cube plus go on and on and on, plus 1 by I factorial a to the power I t to the power I, and that's it. So now if we finally want to write the solution of the state equation, okay, so hence the solution of the state equation, solution of the state equation, this can be written as x of t is equals to e to the power at with your initial condition. Okay, so this is your state equation solution. So now this was without input. We have not applied any input in your state equation. If you see your differential equation starting from here, you don't have any input quantity. It's a state matrix A, x dot t is equals to A of xt, and that's it. You don't have the u part in it. Okay, so these kind of equations are known as homogeneous equation. Okay, this is your homogeneous equation, and that's your solution for homogeneous equation. So where your solution of the state equation, which is homogeneous in nature. So where you don't have input, that's your homogeneous equation. Okay, so this is your solution. Now next we will see what if we include the u part. What if we include the input part also? Okay, so let's see that when we have the state equation of nth order. Okay, so nth order state equation, nth order state equation with the input. So it will be your non-homogeneous equation. Okay, non-homogeneous equation it is, and it can be written as x of t x dot equals to ax plus bu t, a of x of t plus b. Excuse me. And this is with the initial condition x of 0 is equals to x0. Keeping it as this is your equation number 12 here, and that's your equation number 13 here. So I'll keep it as equation number 14 in our case. Okay. So this is the equation, and we would like to solve this equation and find the solution for this, where your x0 is nothing but initial condition vector. Now the state equation given by equation number 14. Now this can be rearranged a little bit as x dot t minus axt equals to but. Okay. Now if we pre-multiply both sides of this equation by e to the power minus at, then we would get e to the power minus at multiplied with x dot t minus axt is equals to e to the power minus at but. This is what we get. Okay, we further simplify it, e to the power minus at x dot t minus e to the power at to the power minus at multiplied with a of xt is equals to e to the power minus at multiplied with but. So this is what we have, and we can also do something little bit for some similarity. We can do it like this. I'm multiplying the minus inside with the a and keeping it plus here. This for the easy simplification. Now as we know that the differential of now we will consider the differential of e to the power minus atx of t. Okay, so the differential of e to the power minus atx of t can be d by dt of e to the power minus at. We will differentiate this term, okay, and we will see that it can be written as e to the power at x dot t plus e to the power minus at minus of a of x of t. Okay. So now this is having some similarity here, right? So from these two equations, so let me just number these two equations. I'll write it 15 and I'll write it 16 here. So by combining 15 and 16, I can write a new equation here, that is d by dt of e to the power minus at x of t equal to e to the power minus at e to the power a minus at b ut. Okay. Now I'll do a little bit of simplifying differential equation thing. So d of e to the power minus at xt equal to e to the power minus at but and dt. So I have taken this dt this side, and now what we do the integration part. If we integrate this equation number 17 between the limits of 0 to t, so integrating, here we are integrating the equation 17 between the limits 0 and t. So if we do this, then we will get the expression for e to the power minus at. Okay, so your e to the power minus at xt will be equals to nothing but x of 0 plus integration over 0 to t, 0 to t, 0 to t, integration over e to the power minus at b ut dt. Okay, so now this 0 to t I can write it as tau. So d tau it will be. Okay, this is tau. Okay, let me clearly write this tau. I'll rub it and rewrite this tau like this. Okay. So this is my equation number 17 rewritten after integration. Okay. So here your x0 is nothing but the initial condition vector. Initial condition vector. Okay. And that's your integral constant also. And your tau is nothing but dummy variable substituted for t. Okay, so that's dummy variable substituted for t. Now, if we pre-multiply both the sides by e to the power at, okay, now we pre-multiply both the sides by e to the power at, we will have an equation like e to the power at multiplied with e to the power minus at x of t equal to e to the power at x of 0 plus e to the power at integral over 0 to t e to the power minus at but d tau. Okay, so that's d tau, and this goes off. Okay, and x of t remains as e to the power at x0 plus e to the power at 0 to t e to the power minus at b ut d tau. And that's it. That's our solution for the homogeneous equation. Sorry, that's our solution for non-homogeneous equation. Now here the term e to the power at is independent of the integral, independent of the integral variable tau. So your e to the power at can be brought inside the integral function. Okay. So if we want to do that, if we see here right now, this is the case. And if I want to number this equation, I can number this as equation number 19. And so as we know that EAT is independent from the variable tau. So we would not like that to happen. So we would want that dependency on tau. Okay. So as we know that we have this term x of t e to the power at x0 plus e to the power at, and then this whole term which is dependent on tau. So this term has to be dealt. Okay, so we'll bring this term inside this particular integral term, and we'll rewrite this x of t. So your x of t will become something like this. Your integral from 0 to t, and your EAT e to the power minus a tau. This is tau all the time. Have I written t? Yeah. So this would be your tau everywhere. Pardon me for this mistake. Okay. So yeah. So from here, we'll write bu tau. Yeah, this is also tau. This all would be tau inside integral d tau. Okay. And I can finally write this as x of t is equals to e to the power at x0 plus integral over 0 to t e to the power a t minus tau b u tau d tau. And this is my final solution for a non-homogeneous state equation. Okay. So we have seen the solution for state equation without input, and which is this. State equation without input is this. That's homogeneous equation, and this is the solution. And state equation with input is this, with initial condition vector, and its solution is this. Okay, so now here we have the concept of state or matrix exponential. That's our matrix exponential. So now the state transition matrix, which is matrix exponential, is this e to the power at state. This is known as state transition matrix, ST. State transition matrix. Okay, so this e to the power at is denoted by a symbol as phi of t. Okay, so that state transition matrix denoted by this phi of t. So basically this means that this implies that phi of t is equals to e to the power at, and if you have any delay in this t terminology, so that would also be reflecting in this denotation. Okay, so for example, if you have e to the power at t minus t0. So that will be represented as phi of t minus t0 is equals to e to the power a of t minus t0, something like that. Okay, and similarly, sorry, this minus would not be here, and this would be your only 8. Okay, so similarly, you have, for example, phi t minus tau can be written as e to the power a t minus tau. Okay. So this equation, this equation number, what number we are giving it? Let's give it as equation number 20. This equation number 20 can be rewritten in terms of phi. Okay, so you can write it as x of t is equals to phi t x0 plus integral over 0 to t phi of t minus tau b u of tau into d tau. If the initial conditions are known at t is equals to 0, then you write it like this. If the initial conditions are known at t is equals to t0, okay, so then you will have a real different version of it is equals to, which says that x of t phi of t minus t0. Sorry, it's little getting messed up here. So it would say phi of t minus t0 x of t0 plus integral over 0 to t, integral over t0 to t. Here it was 0, right? Here it is t0. So integral over t0 to t phi of t minus tau b of u tau d. So this is your general solution and general representation in terms of phi t. That's the state transition matrix. So now there are several properties of state transition matrix. Okay. So I'll just briefly write down those properties. Properties of state transition matrix. You all would like to know more about the properties of state transition matrix, so please, there are many good books of control systems which is covering modern control engineering. You can go and see the proofs for the details, but for basic properties of the state transition matrix, one of them is if phi of 0 is there, then it can be written as E of A into 0 times. And that means nothing but it's your identity matrix, which is unit matrix. Okay. So that's one property. And why these properties are important? These properties are important when we solve for, when we compute for state transition matrix, or when we are solving numericals in modern control engineering, when we are working on the different theories of linear systems in modern control engineering. These properties makes the simplification steps a little bit easier. Okay, so that's phi of 0. Then we have phi of t equals to e to the power at. Okay, and it is also equals to e to the power minus at multiplied with power minus 1. Okay. And this can be further written as phi of minus t to the power minus 1. So that denotation exactly goes like e to the power at is phi t, e to the power minus at is phi of minus t. Okay, so that's your second property. Now this whole thing can also be written as phi to the power minus of t is equals to phi of minus xt. This can also be written. Then if you have a phi of t1 plus t2. So this can be written as, in terms of exponential, it can be written as a to the power a of t1 plus t2. This can be further written as a of e to the power a t1 multiplied with e to the power a t2. And now further going on, phi of t1 multiplied with phi of t2. That's basic. From the basic denotation understanding, this is what we have. Further, in the next class, we would like to discuss computation of state transition matrix by using different methods, or we would also like to solve some numericals. So this is it for today for the solution of state equations with input and without input. Thank you all for watching this video, and if you have any doubts, you can drop them in the comment box. Thank you. That's it.